Hello, I welcome you all in this presentation related with the subject failure analysis and prevention, and we are talking about the fundamental sources of the failure as a part of the failure analysis, so that we can get the idea about the directions in which we can look for the possible sources of a failure. And in this connection we have talked about the deficiency in design, improper or imperfections in the material, and now we are talking about the improper manufacturing conditions or deficient manufacturing or the processing conditions. In this under this heading also we have talked a lot about the various aspects like the manufacturing process or the improper selection of the manufacturing process parameters. Today we will be basically taking up the failures which are caused by two steps related with the manufacturing. One is like indentation marks. During the manufacturing, frequently the batch marks, product number are marked. So, if that is produced by the indentation approach or by engraving using the electrochemical related processes, then these indentation frequently become the source of the failure. So, we will be talking about that little bit in detail, and thereafter there is another aspect that if for enhancing the properties, for improving the mechanical properties of the products made by the manufacturing processes like casting, welding, forming and machining, if subsequently further improvement is needed, and also to relieve the residual stresses, if we have to perform the heat treatment. So, if the heat treatment conditions are not selected properly, or the various aspects related with the heat treatment are not chosen properly for this treatment purpose, then that also can lead to the premature failure of the component. So, in this presentation basically about these two aspects we will be talking about. So, here if we take up the first indentation marks, there are two basic approaches which are normally applied, like one is, you can say, the mechanical based approach, where either we can use the indentation and we can use the embossing also for this purpose. Embossing is primarily applied in case of the sheet metals, while in case of the heavy sections, the indentation using the punches, these marks are applied. Then there is a electrochemical based method which is normally termed as electrochemical etching, which is about the controlled removal of the material from the component on which the marking is to be done, so that it can produce the required numbers or the letters. So, numbers like alphabets A, B, C, D, or number 1, 2, 3, 4 or anything else also can be placed. So, these are the two approaches which are used for the indentation purpose. The thing is, like whenever the mechanical based approaches, like in heavy sections, the punches are applied for producing the indentation. So, application of the indentation using suitable punch displaces the material sidewise for producing such kind of marks. So, such kind of the displacement, basically displacement of the metal for the indentation purpose by using the punch causes the plastic deformation of the material, and if the metal is work hardenable, then it tends to get hardened. So, the formation of such kind of indents, especially in high stress areas, like this is the shaft, and if the shaft is marked with some of the indentation mark in at the surface. So, if such kind of marks are located in the high stress zones which are critical for the performance of component, then these marks will be acting as a huge stress raiser stress razor, and such kind of the stress razor can increase the actual stresses acting at those locations, and can easily nucleate the cracks, and which under the subsequent loading conditions can grow or propagate and to cause the premature fracture. So, basically the indentation, mechanical indentation using the punches sometimes hardens, and if at the same time it also acts as a stress razor, because some kind of the irregularity in cross section is created intentionally. So, there are two aspects which are related with. One is the stress concentration due to irregularity being created, and the second one is the hardening of the metal around the locations where this kind of punching is done or indentations are being applied for marking purpose. So, hardening of the metal will also be reducing their tolerance for the growth of the crack, nucleation and growth of the crack. So, a combination of both these factors will be providing easy nucleation and the growth of crack, which can lead to the failure of the component, since especially in those components where the stresses acting onto the surfaces are maximum. So, such kind of the components are like a shaft or a springs, where the surfaces will be having the higher magnitude of the shear stresses, torsional stresses, as compared to that of the those which will be acting at the in the core. So, indentation marks are basically more harmful for those components where the surface stresses are higher than those which are acting in the core of the component, and they get hardened rapidly due to the indentation marks. So, if the marks are deeper, then irregularities being imposed due to this indentation will be providing the easy stress razors for stress concentration, which will facilitate the nucleation and the growth of crack, and which in turn will be leading to the premature failure. And we know that the nucleation and growth becomes easier and faster, especially if the load is not static. Load is not static, but it is dynamic. Like the load is fluctuating, say the fatigue loading or the impact load conditions, such kind of the stress razors become more harmful, because the time available is not much for the stresses to get relaxed due to the localized yielding, and therefore, if such kind of this stress razors are present in form of the indentation mark, then under the fatigue and impact conditions, such kind of the marks will be facilitating the nucleation and growth of crack easily, and therefore the presence of the indentation mark, especially in high stress areas, become more harmful. So, that is what has been shown in this diagram also. Here what we can see, this is the shaft on which indentation marks were present in form of the date on which it was manufactured, and at the periphery of this number we can see which acted as a site for the nucleation and growth of the crack. And this is how it works in severe localized deformation, electrochemical etching. These increase the stress concentration, especially where these letters have been made, and these will be increasing the actual stresses. This is what we can see, how the cracks at these locations, how the fracture surface is created. These will be providing the easy site for the nucleation and growth of crack. So, this is the location where such kind of the crack has grown in the first stage, and thereafter a second stage, followed by the third stage for catastrophic fracture for the indentation marks. So, as I have said, indentation marks, especially in high stress areas, are harmful, and especially in the metal systems which are hard, brittle and are of the low ductility, because such kind of metals do not provide the localized yielding easily. So, absence of the localized yielding maintains the stress concentration, and which in turn increases the chances for cracking, and such kind of things especially happen in the hardened heat affected zone or hardened steels having the hardness greater than 50 HRC. So, these kind of the indentation marks are more harmful for those situations. Another as I have said, another important step in manufacturing process is the heat treatment. We know that heat treatment is used for variety of purposes. One is primarily to improve the mechanical properties through the control of the microstructure of the metal, and the second purpose is also to reduce or relieve the residual stresses if they have been produced in course of the manufacturing. So, reducing the residual stress, and when it is performed, there are so many other secondary benefits which are obtained, like the more or increased stability in terms of the properties, more uniformity in properties, and also increased dimensional stability is achieved if the component is especially to be exposed under the high temperature conditions. So, the heat treatment helps otherwise in number of ways. The simple steps which are used in heat treatment, if you have to generalize the procedure which is used for the heat treatment purpose, will depend upon will depend upon the type of metal system which is to be used and the purpose for which heat treatment is to be applied. But in general, in the heat treatment, if we see the thermal cycle which is applied, in y axis if we have temperature, and in x axis we have the time, which maybe say we can write in minutes, and here it may be in degree centigrade. So, initially the things the component to be heat treated is heated slowly, not at very high rate, so that the temperature of the entire cross section of the component is increased gradually and does not lead to the differential expansion during the heating. Otherwise, it may cause the buckling or the distortion in the component, because the surface will be heated at a much faster rate than the core, and that may otherwise lead to the differential temperature, too high difference in temperature in the core and at the surface. So, due to the differential expansion, there may be wrapping or the distortion in the shape of the component. So, the rate of heating is to be optimum, not very high enough, because a high heating rate is harmful. Thereafter, the component is held for a particular period of time, so that the purpose of the heating to the high temperature is solved, and depending upon the heat treatment purpose, depending upon the type of the heat treatment being performed, it may be held at different temperatures. So, according to the heat treatment purpose also, heat treatment type of the heat treatment also, sometimes like for precipitation hardening systems, it is called solutionizing. And in case of the steel, it is called austenitizing. And then it may also be done like for stress relieving. It is like say the stress relieving temperature, So, it is expected that there won't be any phase transformation during the stress relieving, and thereafter as per the kind of purpose, again the cooling rate, different cooling rates are applied. It may be cooled very slowly, or it may be cooled at a faster rate, or it may be cooled at very high rate. So, depending upon the purpose, this kind of the cooling rate is used for the quenching or hardening of the steels, maybe somewhat lower cooling rate is used for the normalizing purpose, and thereafter very low cooling rates are used for the annealing purpose. This is the case of the steel. For precipitation hardening systems, the different kind of heat treatment cycle is used, wherein first we heat to solutionize the things so that homogeneous solution is obtained. Thereafter it is quenched, and after quenching again the system is heated for the artificial aging purpose, and then it is held at that temperature and then again it is cooled. So, depending upon the kind of heat treatment which is being applied, different kind of the heat treatment cycles can be used. So, the point here is our heating rate has to be proper, the correct the solution, the temperature at which it is held, holding temperature, or it is also called soaking temperature, has to be correct, and holding time also has to be, soaking time or holding time should also be the proper one. It has to be optimized as a part of the procedure, and thereafter as per the purpose the different cooling rates need to be applied. So, there are three things basically: the heating rate, and then the heating temperature, or you can say holding temperature or soaking temperature, and then like soaking time, and thereafter cooling rate. So, a proper control over these, proper determination and control over these parameters is required, so that we can get the desired set of the properties. So, inappropriate control over the heating rate, holding temperature or soaking temperature, holding time and cooling rate lead to the such kind of the structures and properties which will be deteriorating the performance or mechanical performance of the component, therefore reduced performance, which in turn can lead to the reduced performance or premature failure or inability to take up the service conditions in terms of the mechanical load or the environmental conditions which will be experienced by the component during the service. And therefore, heat treatment has to be parameters has to be identified properly, and they need to be controlled. And if that does not happen, then the various possibilities are there. One is like overheating. Overheating, there are two possibilities. One is heating to the too high temperature and heating for the too long duration. Both will be deteriorating the things, especially like say if we consider an example of the steel. So, here this is the gamma zone, this is the gamma zone, say this is corresponding to the 0.8% carbon steel, this is corresponding to about 2% carbon steel, here carbon, and here the temperature in degree centigrade. This is iron, basically iron carbon diagram. So, if the steel of say 0.3% carbon is heated say about the 30 degrees and 30 to 50 degrees centigrade above the upper critical temperature, like say this is that. But instead of heating just up to this temperature, if the steel is heated to the too high temperature, then there are various undesirable effects on the properties. And similarly, so this kind of effects may be in form of due to the overheating, it can lead to the partial melting. This happens primarily in case of the alloys, where we have the two phase zone at a high temperature. Say if the steel is of like say iron carbon system having 1.2% carbon, hyper-eutectoid steel, in that case as soon as heating is performed above this temperature, we will have the two phase zone, which is gamma plus liquid. So, heating the too high temperature, at this temperature it will not get to the molten state, but at the steel, if it is of 1.2% carbon steel, it will get to the two phase stage even at the lower temperature. So, depending upon the composition of the steel, correct heating temperature has to be identified, otherwise it can lead to the partial melting of the obviously low melting point phases. And here what it will be basically the eutectic system, which is the laterite which is formed, which will laterite will be melting above the solidus temperature. Apart from this one, if heating to the high temperature for long can lead to the oxidation of the metal surface, it can also lead to the excessive grain coarsening in form of the coarse grained austenite, which can increase the hardenability and produce the martensite in place of the fine perlite, otherwise which will be needed. Excessive prolonged heating at high temperature can also lead to the decarburization. It happens mainly in case of the steel, where the loss of the carbon from the surface of a steel takes place, and that loss leads to the reduction in yield strength, reduction in the hardness, which in turn decreases their capacity to carry the load. So, this is what happens if the heating, if the overheating is done. Similarly, prolonged heating also causes the spheroidization, especially in case of the steel. So, spheroidization is basically the cementite plates, basically they get spheroidized, they form nodules and spherical shaped particles of again Fe3C, or sometimes the graphite also. So, leaving the iron in the matrix. So, basically this leads to the softening of the steel, reduction in mechanical properties in terms of the tensile strength and the hardness. So, unnecessary prolonged heating is also not good, and if that happens inadvertently, unknowingly, then these undesirable effects can be there. As I have said, the partial melting can reduce the ductility and the toughness, can increase the nose sensitivity, and can reduce the resistance to the fatigue and the tensile load carrying capacity. There is another important aspect like the heat treatment. Quenched steels normally subject quenching. After quenching of the steels, steel normally gets hardened. Too high hardness actually reduces the toughness. So, the steel with the reduced toughness finds the very limited use, and they are limited use in the application. So, therefore, it is required that all the quenched steels are tempered. So, tempering will lead to the increase in toughness and the reduction in hardness. So, if we see the typical plot, temperature versus the tempering temperature, basically this is tempering temperature versus the toughness and hardness So, basically the toughness, which is low after quenching, in quenched state toughness is low, and this keeps on increasing with the increase of tempering temperature. On the other hand, the hardness decreases like this. So, we can see that if the tempering temperature is not proper, then we will be having something else. Say for this tempering temperature, steel will have one particular set of the hardness and the toughness. So, this much hardness may not be good enough for the application. So, as per the purpose and the required set of the properties with regard to the hardness and toughness, we have to select suitable tempering temperature. So, this temperature will be giving us this set of the hardness and the toughness. So, here these are the two curves. This is showing the toughness and this is showing the variation in hardness. What we can see here, increase in tempering temperature reduces the hardness and increases the toughness. A different kind of trend is observed, especially in the steels having the vanadium, chromium, tungsten. So, these steels of a particular temperature, they start forming the secondary carbides. So, this is called secondary hardening, especially when for primary hardening is one where quenching helps to achieve the desired hardness, and during the tempering, when these carbides precipitate at a higher temperature, so the secondary hardening is facilitated. So, this tempering has to be done for the correct time and at the correct temperature. Both are not good. Because the under tempering will be leading to there are two words which are used regarding the tempering process. So, over tempering and under tempering. Over tempering means excessive tempering, which will be leading to the reduction in hardness beyond the acceptable level, and reducing the tensile strength. So, both may not be acceptable, and under tempering is the just opposite, wherein the hardness is still high enough then that is required, and the toughness is low enough. So, for any given application. So, it is required that both over and under tempering is avoided, so that we can have the optimum tempering wherein we have the required combination of the strength and hardness for achieving the required mechanical properties in the steel after the hardening. So, inappropriate selection of the tempering conditions can lead to the under tempering or the over tempering, and that becomes the result of, like, say, untempered martensite, which increases the hardness, but at the cost of toughness. Similarly, as I have said, another way by which the failure of the component due to the improper heat treatment conditions can take place is the thermal shock. Like for the heat treatment purpose, and normally from the 800 and above degree centigrade, we have to cool it very fast, and this is in seconds. Like in CCT diagram, if we see, if the too high cooling rate is applied, then it will be leading to the austenite transformation into the martensite. So, if the large components are quenched like this, then surface will be cooled rapidly, while the core will remain at a high temperature. So, such a high difference in the temperature or high temperature gradient at the surface and the core sometimes leads to the quench cracks, or so that will be promoting the surface cracks, and these cracks can lead to the premature failure of the component. This kind of high temperature gradient can also cause the distortion in the components which are of the thin sections and the complex in shape. Then unsuitable recommendation of the unsuitable heat treatment, there are different heat treatment processes, like for steels, like annealing, normalizing, quenching, tempering, then os tempering and mar tempering. So, as per the kind of steel, all these steels may not be responding in the same way to the different category of the heat treatment. So, depending upon the composition of the steels, we need to recommend the suitable heat treatment so that target properties can be achieved. But if that kind of selection is improper, means selection of the heat treatment type of heat treatment to be applied is improper, then we will not be able to realize such kind of the properties. For example, precipitation hardenable alloys like aluminum, copper, titanium alloys, magnesium alloys, etc., they will require different type of the heat treatment, like solutionizing, quenching and then aging, which may be like at room temperature or at high temperature for artificial aging purpose. So, selection of the suitable heat treatment is also important for achieving the desired combination of the properties, which will help us to have the required combination of the mechanical properties for the target performance. Now, we will see that the loss of alloying element, as I have said, a loss of alloying elements may be in form of the decarburizing or the loss of other alloying elements due to the excessive exposure at high temperature in the oxidizing environment. So, such kind of losses of the alloying elements reduces the tensile strength and the fatigue strength, especially in those components which are subjected to the high stress conditions, and the components which are subjected to the high surface stresses like springs and shaft. Then another is the improper control over the parameters, like during the design of the heat treatment we can identify that this will be the heating rate, this will be the cooling rate, and this will be the soaking time. But if the system does not respond accordingly, it is showing the data, but actually the conditions for which the component is being exposed are not according to the design of the heat treatment. So, that kind of thing also can lead to the improper combination of the structure and the properties, which may not be favorable for the applications desired. So, improper heat treatment can lead to the failure in number of ways. Like this is one example where the cracks develop along and during the quenching due to the unfavorable the temperature gradient conditions and the development of the tensile stresses at the surface. These are the two diagrams which are showing that how the loss of the carbon from the surface due to the decarburizing leads to the change in the phases. Here we can see the ferrite and the pearlitic structure, but the ferritic structure which is light etched, white is in color. This is increasing as we approach towards the surface, and this can be seen in both the diagrams, increasing percentage of the ferrite on approaching towards the surface, increase in indicating the loss of the carbon, and we know that ferrite is softer and of the high ductility and of lower yield strength as compared to that of the pearlite, and therefore if the surface is full of the ferrite, then it will be leading to the reduced strength, reduced hardness, and the increased ductility, especially at the surface. So, such kind of the unfavorable structural change due to the loss of alloying elements in form of carbon can lead to the premature failure of the component. This is another example which is showing that how the decarburization, how the overheating simply coarsens the grain structure, and the carburizing leads to the enrichment. Sometimes undesirable induction or introduction, or when the carbon is introduced at the surface of the steel, so too high enrichment of the carbon can lead to the excessive formation of the either iron carbide or the martensite if the favorable conditions exist, which will be deteriorating the mechanical properties, especially in terms of the increased hardness, reduced toughness at the surface, and this kind of thing can also lead to the development of the tensile residual stresses. So, here now I will summarize this presentation. In this presentation, basically I have talked about the two steps related to the manufacturing. One was the indentation and another was unfavorable heat treatment conditions, and the ways by which the inappropriate combination of the parameters can lead to the failure of the component. Thank you for your attention.